exposition is increasing. Right, okay? Then you have to take that one, the negative pixel. Right, whether you are going to decrease the pixel by 1 or increase the pixel by 1, that stay in the same place. Do you understand? Now earlier y position, now here the negative means absolute values are 3 minus 7 means negative 4. 12 minus 2 means positive 10. 4 by 10. That is a negative value, and the quantity is 2 by 5. Negative 2 by 5. Right? Negative 2 by 5. Therefore, it is less than that absolute value is less than 1. Therefore, you can go ahead with normal way. But earlier we have increased, the decision has been taken, this decision we have taken that if this pi plus 1 is, if pi is negative, we plot xi plus 1 and yi. We are keeping in the same place. Otherwise, if pi is positive, we plot I plus 1, xi plus 1, yi plus 1. But here it should be yi plus yi minus 1. Right? Here we have to consider that as yi minus 1. Okay? Understood? Is that clear? That means we are increasing along x direction and calculate y. This condition is going to be yi or yi minus 1. Okay? Is that clear? Yes or no?
Yes, sir.
So that is the way you have to calculate it. And again, that negative sign is available in some cases. So here, delta x is going to be positive value. Delta y is going to be negative value. Right? Delta y is going to be negative value. 2 delta y also, delta y negative value, but we are taking the absolute value. And 2 delta y, again negative value. Right? 2 delta y also negative value. Now here, 2 delta y is going to be negative. Right? 2 delta y is going to be negative. And so altogether we take now here P1 negative, and negative will continue. No? So if this one is negative only, we do this one. If it is positive, when we get positive value, we are going to go for this one. Negative means this one. So the PI will be calculated by using the absolute values. Now here the delta y is going to be not negative 4, positive 4. Delta x going to be 10. And 2 delta y means 8. 2 delta y, 8 minus 2 delta x means negative 2. This is negative. Then you plot this one, right? And you calculate it by using pi negative 2 plus 8. That is positive 6.
Yes, sir.
Right? Yes.
So your screen is not visible, I think.
Sorry. Now can you see my screen now? What I said was, now this is the decision, right? We are considering, yes or no? This is the decision. Okay? This is the decision. And we are decreasing 1 by 1. That is the situation. Now here, when we have the point pi less than 0, we plot xi plus 1, that is always there, yi. If it is negative, positive, then we plot xi plus 1, yi plus 1. Here, instead of yi plus 1, yi minus 1. will be plotted because it decreasing. That trend is there. That indication has to be taken. That indication has to be taken. Right? Now here, when we consider the delta x, delta y, we know that delta y will give you negative result, but we are taking the absolute value. Delta y as absolute value. Therefore, this negative 4 become 4. Because according to the calculation here, delta y is going to be 3 minus 7. That is negative 4. Delta y is becoming that absolute value we are considering, therefore 4. 12 minus 2, 10. 3 minus 7, 4. That is how we are going to evaluate that part. Right? Do you want me to do that here? Do you want me to do it here? Hello? If you want to do it, I will do it. Huh?
Yes, sir.
Okay. Let me share the whiteboard. Okay, now I think you can see the whiteboard, right? Now my situation is starting point and ending points are there. Two comma 7. 12 comma 3. So delta y, I'll take that one as delta. And the delta symbol can be copied and pasted here. Delta y equal 3 minus 4 or 3 minus 7 and negative 4. We are taking the absolute value, then it will become 4. Right? Delta x is equal 12 minus 2, that is 10. Right. So the P1, we start with the plotting by we start by plotting 2 comma 7. Plot 2 comma 7. P1 will be calculated. P1 is equal to normally that normal situation we go to the algorithm, right? Normal algorithm we go, and we can see that P1 is calculated as 2 delta y minus delta x. 2 delta y minus delta x means 2 delta y means here 8. Delta x is going to be 10. So it is negative 2. Negative 2. This is less than 0. Therefore, we plot xi plus 1. Xi plus 1 means 3. Yi means 7. We plot that one. We are not moving from there. And then it says that P2 is calculated. P2 is calculated. P1 plus 2 delta 2 delta y. Right? That is how we calculate the next one if it is negative. So that result is going to be negative 2 plus 8 equal 6. Now it is greater than 0. Therefore, what we do is we are going to calculate it by using this one. Then we plot. It is greater than 0. Therefore, x will be increasing. 4, x will become 4, xi was 1. Yi not plus 1 because it's negative direction, which goes 7 to 3 we are reducing. Therefore, yi minus 1. Therefore, it is 6. Now we are going to calculate P4 or P3. P3 equals 6. The equation is going to be Pi plus 2 delta y minus 2 delta x. 2 delta y minus 2 delta x. Right? Now here it is going to be 6 plus 2 delta y means 8. 2 delta y means 8. 8 minus 20. Because delta x is 10. Delta x is 10. Therefore, 2 delta x becomes 20. Right? So then it will become 14 minus 20. Then it is negative 6. Negative 6 is less than 0. Negative 6 is less than 0. Less than 0. Then we plot 5 comma the same value 6. It was 6. And we calculate P4. P4 we will calculate negative 6 plus 8. Well, positive 2. That is greater than 0. Therefore, we plot by increasing 1, 6, comma. We reduce 1 here. We reduce 1, 6, 7. We plot 6, 7 and calculate the P5. Calculate P5 by taking 2 plus Pi plus 8 minus 20 plus 20. Then it will become negative 10. Negative 10. Negative 10. Right? The value will become negative 10. Yes, negative 10. Oh, sorry, this one should be a negative 1. I miss it. This is 5. We have to reduce 1, 6, and then 6, and it should be 5. And negative 10. Then it will become plot. This is a negative means this is negative. We plot 7, comma, the same value 5. P6 will be calculated. P6 will be calculated. Negative 10 plus 2 delta y. 2 delta y means 8. Again, it is going to be negative 2, less than 0. Less than 0. Therefore, we plot again 8 comma 5. 8 comma 5 will be plotted. And then P7 will be calculated. P7 is going to be negative 2 plus 8, that is going to be 6, and it is greater than 0. Therefore, we plot again 9, we reduce 1 by 5, 4, 9, 4. And we calculate the P8. Here it is 6 plus 8 minus 20. Then again it will become 6, negative 6, and it is less than 0. Therefore, we plot 10, 5, 10, 5 as it is. 10, 4 as it is, and calculate the P9. Negative 6 plus 8 equal negative 2. Positive 2. Then it is greater than 0. Therefore, we plot the same point will be reduced by 1, 11, 5, 3. 11, 3 will be plotted. And then, so now we are coming to the last point that 11, 3 is there. And now we calculate P10. P10 equals 2 plus 8, negative 10, negative 20 is going to be negative 10. Then we plot as it is negative here 12, 3 will be here. Now that's how you can calculate. These are the points which are going to be plotted. So when there is a decrement in one of the direction, you have to take that direction, that coordinates are to be decreased one by one, not one by one increase. Is that clear? Hello? Everyone? How about others?
Yes, sir.
Yes, sir.
Sir.
Right. Let's move to the today's session. I think it's understood, right? So let's move to the today's session. That's good. You asked a question, and I feel that you have tried to do it, right? That's why you came up with these questions, right? That's good, right? I'm very happy about it. And next, we are going to start the 2D weaving pipeline. And still we were not able to do the third one, also a little bit difficult. Third one means starting point negative to -1 and slope is 1.1. So here you have to calculate first 3 points only, right? You have to calculate only the first 3 points. Now the slope is given. slope is given, and if the slope is given, you have to calculate the next 2 points. Here the delta y and delta x is not able to calculate, but you are only going to calculate first 3 points. So if this is the ratio, so then how you can get the -2 and -1, the starting point, ending points are not there. So you have to adjust it to 1.1. That means 6 divided by 5. The 6 divided by 5 means not 6 divided by 5. 11 divided by 10. 11 divided by 10. Okay. 1.1 means 11 divided by 10. May I share that one? So here 1.1 means 11 divided by 10. So here the upper part is 10, 11, the lower part is 10. Therefore, this is starting point. 9 minus 1 is 10. 9 minus -1 is 10. This should be 11, no? 9 minus -2 is 11. 9 minus -2 is 11. Therefore, 9 is the last point. You have to take that way. The first 3 points you have to calculate. It asks only first 3 points. So the same way, so the 9,9 is the last point. That's how you have to calculate. You understand what I said? Huh? That way you have to calculate the first 3 points. Who is asking that question? Let me see. That is also a problem. I know that. Yes, Shaba. Yes, the same person, right? Shaba. Shaba, do you understand that one now? Shaba, do you understand that one now? Hello? Huh?
Can you explain that again?
Huh?
Can you explain that again?
Okay. What I said was actually we have to calculate. The problem here is you cannot guess what is the delta y and delta x, no? Huh? That is the problem, right? Hello? Shaba?
Yes, sir.
Your problem is delta y and delta x. Now here on the slope is given. It asks only first 3 points. Therefore, what you have to do is, you know this 1.1 means delta y is something like 11. Delta x is 10. 11 divided by 10 means 1.1, right? Okay? Hello?
Yes, sir.
11 divided by 10 means 1.1. Therefore, you have to take the upper part is 11 and lower part is 10. And to get the 10, this is -2. Minus -2, it becomes +2. 9 plus 2. 9 plus 2, 11. Then the lower part, 9 plus 1, 10. Is that clear?
Yes, sir.
Huh?
Yes, sir.
So the endpoint is 9,9. Okay? Consider endpoint as 9,9 and calculate the first 3 points. Okay? Are you clear about it now?
Yes, sir. Clear.
Huh?
Yes, sir.
Okay. Then you can apply the algorithm. Little bit tricky things are there. You have to think about it, right? That's good. You have tried it, right? That's good. Okay. Let me move to the today's session, what I'm going to discuss. So today we are going to start with the filling algorithms, right? And 2D viewing pipeline after that. First, I'm going to discuss about filling algorithms. Now, let's see what are these filling algorithms are, right? Let's see what are these filling algorithms are. Right. Now, what is this filling algorithm? Now, when we have a two-dimensional graphics, for example, we have already started the CorelDRAW. In the CorelDRAW type of vector drawing mechanisms, we draw the outline shape, and we will be able to draw the fill the inside with some kind of color. Now, when we ask this program or tool in the applications, right, graphical applications like CorelDRAW, Photoshop or something, when we ask, for example, we draw something, and when we want to fill the area, sometimes by using paint bucket type of applications are there, right? We take it and fill it. When we ask to fill it, that filling program should be able to fill only the area which we want to fill, that is the inside area. Now, today we are going to start discussing about how these filling algorithms are working. Filling programs are working in this type of tools. Now, area filling algorithms are normally used in most of the time in vector tools like CorelDRAW, Illustrator type of application tools. Those are some applications. So inside those applications, these type of tools are available to fill the areas. So filling is a kind of a mechanism which we work in a raster fashion. Row by row, we should be able to fill it. Row by row, we should be able to fill it. Now, when we are filling the area, we should be able to know, now the problem is whether these pixels are inside that particular area or outside that area. We have to take a decision on that. අපි දැන් පික්සල් එකක් ෆිල් කරනකොට යම්කිසි කලර් එකකින් මේක ඒ රූපය ඇතුලේ පික්සල් එකක්ද එළියේ පික්සල් එකක්ද කියලා හඳුනා ගන්න ඕන අර ටූල් එකේ. Then only that tool can fill the area. Right? Now, for that purpose, there is a basic algorithm available. We call that as a scan line algorithm. Scan line algorithm. Let's see how this scan line algorithm to fill. Now, for example, if this is the diagram, we want to fill this area, that filling has to be applied only for these pixels, not outside pixels. මේක එළියේ fill කරන්න fill වුණොත් ඒක වැරදි. මේක ඇතුලේ විතරයි fill වෙන්න ඕන. So how are we going to decide by that algorithm whether it is inside or outside? Right. Let's see how it works with the parity fill algorithm. The parity fill algorithm, what it do is it go line by line. For example, line, when you take one line, and it will mark it as odd, even, and odd, even. One bar after the other, the odd and even will be marked. How it marked? When this line goes across that particular boundary. දැන් මේ boundary නේ ඇදලා තියෙන්නේ, boundary pixel එක අපි දන්නවා. When this scan line pixel by pixel we move, one by one we move here, and we come to this particular pixel. When we come to this pixel, when we see that one as a odd parity, we mark it as odd. Next, again we are crossing over another boundary. That will become even. Again, next one is odd. After that, even. So odd, even, like that we mark it. Then what we do is, for odd to even, all the pixels will be filled. Even to odd, from here to here, we are not filling. That is how we do the parity fill algorithm. The parity fill algorithm will mark whether it is odd or even parity odd, even parity marking will be done. Odd to even will be marked and filled. Even to odd will not be marked and filled. Even to odd not will be not marked and filled. And finally, you will get the result as filled area, right? Filled area will be the result you are getting. So the raster line by line we scan and mark this odd even. That is how this odd parity fill algorithm works. Is that clear? Is that clear? Yes or no? Hello? Is that clear? Okay. Now let's move to the next one. Now the problem is available within this algorithm. Let me show you that problem. I will use the same mechanism. Suppose that corner point is available here. Now I am going ahead with the corner point. Now how I start? Here it is odd. Here it is even. Again here it is odd. There is no any other point. Here it is even. And here it is odd again. Odd, even, odd. Now what is our rule? Odd to even fill. Here it is fill. Odd to even fill. That means here we are going to fill this area. But it is incorrect. When there are corner points like this, again I am telling another one. Here it will become odd. Here it will become even. And we are going to fill from here to here. But it is incorrect. At the corner points, this algorithm fails. At the corner points, the algorithm fails. If there are no corners, this algorithm will work fine. Nicely it will work. If there are no corners. If there are corners, this algorithm fails. So what are the disadvantages? It's only work properly for ideal primitives. Ideal primitives means circles, rectangles, those type of primitive shapes, it will work. Other shapes like, non-primitive shapes, cake with shapes and lines parallel to the scan in direction. There are lines parallel to the scan in direction. It will do a kind of a marking, odd, even, not even, not even for a continuous manner. If there are boundary lines available parallel to the scan line. හැම එකක්ම boundary එකක් හැටියට ගන්න ඕනේ. ඒ line එකේ තියෙන හැම pixel එකක්ම boundary එකක් හැටියට ගන්නවා. එතකොට odd even not even දාගෙන යනවා. Right? That is also not correct. And does not work properly for self-intersection figures or self-intersection points. Right? Advantages are listed like fast, very fast. It can be implemented by hardware-based algorithms. And most packages does not allow self-intersection figures, therefore it will work. And only primitive shapes are available. Most of the application packages, nowadays you can do many things. Parallel line doesn't occur very frequently, and if they are simply ignored, parity fill gives you a very good result. Now next one is the scan line algorithm. Now to overcome these problems, there is another algorithm introduced that we called as scan line algorithm. Now what was the problem we had in the parity fill algorithm? In the self-intersection points means points like this, we had error. Because we are putting odd and even is coming in another side. So therefore, in the scan line algorithm, what we do is, when we get into a boundary, we are checking another condition. Now assume that we are going in this way. When we get into a boundary, we check, we put number 1, and next boundary we put 2. And each and every boundary, we are checking whether that is a corner point or not, or the self-intersection point or not. How to check whether it is a self-intersection point or not? The corners are always available this way or this way. Therefore, when we have the pixels, here, now here also we have pixels. This is marked, and other 2 are not marked. Other 3 are not marked. Right? So here, if we have this type of shape, that means if the other pixels going up direction, the pixels are not there. Those are not filled. Therefore, the continuity is not available. When you mark from one pixel, if the continuity is not available in the upside, if the continuity is available in the both side of the downside, then we mark that as a kind of a cone. This one also the same. If we get 3 by 3 area, 3 by 3 area, then the other one also get this type of, this is marked, this is filled pixel. This may be the quarking pixel here, the odd or even that corner pixel. This may be there, or whatever the thing is available. Only upper side. Here downside is here. Therefore, this is a very good indicator to identify whether it is corner or not. But it needs some calculations, or it needs some comparisons. We have to do some calculations and comparisons here. So when we get into the boundary, we check this condition. We check whether it is a corner point or not. If it is not a corner, we are putting one number. Or that 1, 2. Then here it is 3. When we put the 3, at the same time we check whether it is a corner. Yes, it's a corner. If it is a corner, what we do is at the same time we put another number, 4. And here it is not a corner, 5. And here it is 6. Now what we do is, the algorithm says, from odd numbers to even numbers, draw, fill. We fill these things. Even to odd, do not fill. Odd to even, fill. That means only filling this part. Even to odd, do not fill. And odd to even, fill. That is how the scan line algorithm works. But there is an additional part coming from the parity fill algorithm. We are checking whether the boundary is a corner or not. Let's see how it works for this one also. Now this is upper level of corner. The same thing happens. Whether it is a corner, yes, 1 and 2 also put here. And here 3, 4 also put here. Now it is not a problem. 1, 2, 2 to 3 we will not draw. 3 to 4 we don't draw. That's how it be. So that's how we work here. That's how we work here. Right. So what are the advantages? Right, let's see what are the advantages. Right. So the odd numbers to even numbers do the filling. Even numbers to odd numbers do not fill. That's the algorithm works. That is the rule of the algorithm. And advantages are does not take up much memory to store these things. Good for transparency and shading as well. Makes good use of coherence, and we can do it. But only thing is, compared to the parity fill algorithm, we are doing some kind of additional checking for those corners. For these corners, the additional checking is happening. Here you can see odd to even will be filled and even to odd will not be filled. So that's how it happens. Is that clear now? Is that clear and understood? Yes or no?
Yes, sir.
Hello?
Yes, sir.
Okay.
Yes.
If we know the parity fill and scan line algorithm for the filling, now we are going for another algorithm, pane bucket type of algorithm, or seed point based filling algorithms. This is a kind of a, area filling algorithm which are famous for many of the applications like CorelDRAW and Adobe Photoshop. You have these filling algorithms. So pane bucket algorithm is working in this manner. And also if you look at this algorithm can be transformed or converted into that magic wand tool type of algorithm also. Magic wand tool type of algorithm. And these type of algorithms work as recursive algorithms. Let's see how this algorithm works in 4 or 8 connected neighbors. Let me tell you how this algorithm works. Suppose we have drawn some kind of a shape. The shape is there. Now tell me how that pane bucket works. Have we done the pane bucket here somewhere? Do you know what is pane bucket? Do you know what is pane bucket? Hello? Pane bucket in Photoshop and CorelDRAW. Do you know that? Yes or no? Okay, the pane bucket is a kind of a tool you have. What you have to do is you have to take a color with the pane bucket and bring it to the area what you have marked. Bring it to the area what you have marked. And then what you can do is you can click on one of the point here. Click on the one of the point here with the pane bucket. One of the pixel. And suddenly this whole area will become that color. Normally this point we called as seed point. Seed point. We call this point as seed point. We apply that pane bucket into this particular point, seed point. Right? And now when we come to this point, let's see how from that point, this is the boundary. Now this is the boundary or border. Or border color. These pixels are having the border color. Now you are filling some other color. Right? Border color or boundary color. We are using this border color, which is available in the border, as a decision parameter. Let's see how it works when you start from the seed point. Now here we have a certain pixel grid. Pixel grid, how many pixels are there? 3 by 3, 9 pixels available. 9 pixels. Now assume this seed point is here. Center pixel is seed point. Center pixel is seed point. Now this algorithm has to decide whether to fill that pixel or not. Whether to fill that pixel or not. That decision is taken solely by considering whether it is a boundary or not. the other condition is we take the boundaries top, bottom regions. Top, bottom regions. And if we are exceeded that top, bottom regions, we are not going to consider that pixel. If we click on somewhere here or somewhere else, we are not going to consider. Seed point is always considered as the point which is inside this particular drawn area. That's how it works. Let's see now that when we click on the paint bucket somewhere, some pixel, how that will work. Now here we have seed point, the boundary is available, the boundary color is some other color. First we are going to discuss about an algorithm called boundary fill algorithm. Boundary fill algorithm. Let's see how the boundary fill algorithm works. The boundary fill algorithm, what we can see is that we have 3 by 3 pixel area. The center pixel, if we take an xy, this is going to be x minus 1y, x plus 1y. Y is this direction, and x is this direction. Y is here, sorry. Right. Now we have clicked on this one seed point, and here you can get consideration into 8 connected neighbors or 4 connected neighbors. 4 connected neighbors means only these 4. 8 connected neighbors means all the points. Let's see, there are 2 algorithms, 8 connected neighbors algorithm and 4 connected neighbors algorithm. Here the 4 connected neighbors. Here we are considering with 8 connected neighbors. Now I think you may have already learned about the recursive algorithms in the web programming or in the normal programming. You may have learned recursive algorithms. What do you mean by recursive algorithm? The same algorithm calls within that algorithm. A algorithm එක ඇතුළෙම A algorithm එක call කරනවා. A function එක ඇතුළෙම A function එක කතා කරලා ඒක වැඩ කරනවා. So we are writing, because those are very fast and very efficient algorithms, recursive algorithms. Therefore, we are going to call this type of boundary fill algorithm. Boundary fill. Now, in this boundary fill algorithm, what we do is we have parameters integer x, y. Those are the coordinates of a given pixel. X kandanke, y kandanke given here a pixel. Okay? Integer fill means what is the color we are going to fill. Color value, that is also integer. Color value to be filled. Then we have integer boundary. That is integer boundary means boundary color value. That also integer number. All the colors are represented by using integers. No? So the fill color and boundary color both are available there. Now what we are looking at is if the x coordinate of that pixel is less than 0 or greater than or equal raster width. Raster width means, as I mentioned earlier, this width area. Here we have coordinates, here also we have coordinates. X and y coordinates are available in the 4 boundaries, right? That full bound. So if it is greater than raster width or less than x 0, we are stopping it. We are not doing anything. We return. We don't fill. And we are checking not only that, whether it is less than y 0, y is less than 0, or y is greater than the height of the graphic. Given area about that particular graphical area, whether we are outside. Then also we are returning, we are not doing anything at all. We are returning. Then we are taking the current pixel. Then we are taking current pixel. Current pixel means current pixel value. Now we are available in the one of the pixel. That is, here we are taking the xy value. Assume that xy value. The seed point or whatever. Raster get pixel value x comma y and put that as current. මේ දැනට මම ඉන්න pixel එකේ color එකක් තියෙනවා නම් ඒක ගන්න කියලා තමයි කියන්නේ. That will be taken and put into the current. If both these conditions are not true, we are coming to the filling, whether we can fill or not to be decided. Then we are checking if current is not equal to the boundary. If my current value is not equal to the boundary color value. If my current pixel value is my current color is not equal to the boundary color. If it is not equal to the boundary color and my current color is not equal to the filled color. My current color is not equal to the filled color. Right? Filled color. If both these things are not satisfied, if both these things are not satisfied, if both these things are not satisfied, then if both these things are not satisfied, then what we have done was actually we say that it is not a boundary pixel. If it is not a already filled pixel, අපි මොහිත කලින් එක fill කරලා දන්නේ නැත්නම් fill color එකේ මේ fill කරලා කරලා තියෙන color එකේ. If the current pixel color is not the filled color or current pixel is not a boundary color, then what we do is we fill that pixel here. We set that pixel with the fill color. We are not stopping there. Again, this boundary fill will be called to the four connected neighbors. Four connected neighbors means these neighbors. X minus 1 y, x y plus 1, x plus 1 y, x y minus 1. X plus 1 y, x y plus 1, x minus 1 y, x y minus 1. Fill boundary, we call again. So for the four connected neighbors, we are calling the same algorithm. The algorithm is this one, the name. We are calling it's inside the same algorithm. That's why I call you this one as a kind of a recursive algorithm. Recursive algorithm. This is in the normal C and Java mode of representation. This is the fraction of that algorithm available and how it works. It's a recursive algorithm. We are calling the same algorithm from itself. The same function from itself, recursive function. We are having recursive function. Now, this function check whether it is boundary or not, whether it is filled or not, and we fill it. And first condition what we check is whether it is outside the area. Now for the same thing, we can extend it to 8 connected neighbors. We can extend it to 8 connected neighbors. What we have to do? Here, instead of this 4, we have to put all 8 with this algorithm. And those pixels also filled. Now that will grow very quickly until you reach boundaries. When you reach boundaries, what will happen? You are not coming in here. When you go outside the full canvas, then again you are stopping. So many threads are working in parallel. In parallel, you will fill it, and very quickly this will grow. The first pixel will be filled, and 4 pixels are there. The 4 pixels will become 16 pixels. 16 pixels will become around 64 pixels. Like that, it will grow like 4 times. So like that, it will grow in a larger manner, and very quickly it will fill the area. Even when you are applying that tools, what do you call this, paint bucket tool in Photoshop, and also fill tool in CorelDRAW, it will happen. It will do that filling very quickly. You do not see that will grow anything. Very quickly it will happen because these are recursive functions. Let's take another version of that one. Here we call this one as flood fill algorithm. Flood fill algorithm. Now earlier one was actually boundary fill algorithm. The boundary is the condition we are using to terminate the threads, right? Terminate the threads by boundaries. When there are boundaries, you terminate that thread when you reach the boundary. Now the situation is you are considering whether it is filled, or all color. Now the flood fill algorithm works when there is an area. Here the area is taken with some kind of a color. Only this particular area to be filled. That is marked area to be filled. You want to fill this marked area. That marked area having some kind of a color. That marked area having some kind of a color. Right? The marked area having some kind of a color. Now, here in this case, actually, what we do is when the marked area having some kind of a color, that color will be taken as all color. Now that is what we call as all color. This is a color to be filled. This is a color replacement. තියෙන color එකක් තෝරගෙන ඒ color එක වෙනුවට වෙනත් color එකක් දාන එක තමයි මේ flood fill algorithm එක කරන්නේ. So we replace existing color with a new color. So we have to give what is the new color to be filled. That is the old color, and that all color areas will be filled. Again, we are checking whether we are outside the canvas or not here. The given point. If raster get pixel xy equal all color, if my current pixel means this one, if that one is equal to the old color, then what I do is I fill it with new color and apply the same algorithm, flood fill algorithm, again to the neighbor pixels. Again, I'm calling for the neighbor 4 pixels. Like that, it will also go like. Now, this is a color replacement algorithm. Here, a color එක කළුත් color එකකින් fill කරන algorithm එක color replacement algorithm. Right? This is work in that fashion. This is a color replacement algorithm. Here, now earlier what was actually 4 connected neighbors. Now here we are coming for the 8 connected neighbors. The same thing, only the coordinates are different. All 8 connected neighbors are available here until x plus 1, y plus 1. Here, x plus 1, y plus 1, x minus 1, y plus 1, x minus 1, y minus 1, x plus 1, y minus 1. All connected 8 neighbors are used to be filled here. Right. So are you confident with this filling algorithms now? Are you confident? Yes or no? Okay. Now we are coming to another very important part in the two-dimensional graphical clipping. The weaving pipeline, graphical weaving pipeline, before any graphic come to you onto the screen, now on the screen, you see something, no? The things what you have, the computer want to show you need to be decided. The real graphic may be very big one. The real graphic may be very big one. So that graphic is available in the memory. That real graphic is in the memory, and that is a very, very big one sometimes. From that graphic, whether that computer system able to show everything or part of it has to be decided by the computer. Whatever the graphic available on the pixels once it generated is available here, the full area. The full area is available here. Now after that, the computer has to generate a window which is possible to show on the screen. A window which is possible to show on the screen. So that window is selected. What is the rectangular area which is to be shown on the screen? That we called as window. We mark the window to be shown. That is based on the window assignment or the selected area from that graphic. Now what is going to happen for this area, other areas? You are not going to consider that. This process we called as clipping process. We call this particular process as clipping process. Clipping. Here, clipping process. And after that, this window is available as a small menu, the window available or hanging on somewhere like this. A screen window area or viewport area. Actually, what we call this one as a viewport. Viewport. From now this graphic what we have clipped to be shown on this viewport. Then those pixels which are already clipped are on this window, that sizes of this window and this viewport may be different. This may be 1000 pixel width. Here the viewport got only 100 pixels or maybe 500 pixels width. Like that, their dimensions are different. Based on that dimensions and based on the scaling, this window pixels, all the pixels which are on this window to be mapped onto this viewport, the selected area or kind of a screen. This is like you have a big screen, the window, some kind of a screen. On the same screen, you have some windows open, right? You are telling them as windows. Actually, those are not windows; those are viewports. Your Microsoft Word small area is available. Another graphic area is available. Different areas you are opening with different applications. In Photoshop also, you can open multiple pictures together. Those are viewports. In the multiple menu, this type of closing, opening, and all this maximizing, all these things are there. That is a viewport we are. So, for example, multiple cameras can be there. Those are multiple viewports. Those are coming from different areas. Now, the world coordinate area is available here. World coordinate area available here. Here we have world coordinate system. Here we have Windows coordinate system. Windows coordinate system. And this is viewport coordinate system. Right? We have world coordinate system, Windows coordinate system, and viewport coordinate system. Now, in the memory, what we generate is world coordinate system. All the graphical area will be examined. And out of that, we select the area which is on the window, selected area. And then map that area to a viewport on the screen. Then that screen is showing this viewport. Right? So the viewport is the rectangle on the raster graphic screen, is defining where the image will appear on the screen. You can take it here and there and drag. Window is the rectangular defining the part of the world coordinate system we wish to display. From whole graphic, whatever the area you want to display on the screen. And clipping is the process of removing the outside or eliminate the outside graphical area which is outside the window, we call as clipping. Now, first what we do is from the world coordinate in the memory, we clip the area we want to show. That clipped area then will be transformed into viewport and we will show it in the viewport. So this is kind of a step-by-step process. Now, where these viewport coordinates are available? The viewport coordinates are inside from here, these pixels can be given Windows coordinates, 0, 0 here. And these pixels can be given viewport coordinate, 0, 0 here. With respect to the screen, suppose this is the screen. With respect to the screen, you can give normalized device coordinates. Normalized device coordinate to the viewport, where you are going to keep the viewport. ඒ කියන්නේ screen එකේ left of corner එකට බිඳුවට සාපේක්ෂව වාගේ viewport එක කොහෙද තියන්නේ කියලා ඔයාලට කියන්න පුළුවන්. එතකොට viewport එකේ බිඳුවට සාපේක්ෂව අර ඒකේ තියෙන pitch එක කොහෙද තියෙන්නේ කියලා කියන්න. එතකොට මේ coordinate system දෙකක් තියෙනවා. You have to understand the screen coordinates and the viewport coordinate system. If you take a pixel here, this coordinate is given from the viewport coordinate system like this, as well as you can give the points here. Here we have the points coordinates to this one with respect to the screen, and we can calculate the point here to here as well. This is going to be the normalized device coordinate. According to the device, ඒ කියන්නේ අවසානයේ මේ screen එකේ display කරන්නේ device එකෙන්. Device coordinate is derived through the viewport coordinate. Where you are going to keep the coordinate of the viewport. Viewport එක එහාට මෙහාට ගෙනියන්න. Right. Is that clear and understood? Yes or no? The generic process. Huh? Yes, okay. Now, window and viewports, actually, there are measurements we take. Most of these measurements are taken by using our pixel coordinates, pixel numbers. Here we have windows. According to the window 0, 0, that set window, x minimum, xw maximum, we can define the window, yw minimum, yw maximum, and those are the only coordinates we need, because we can have 4 coordinates by using these 4 points. What is here? xw min, yw max. Here, xw max, yw max. Here, xw min, yw min. Here, xw max, yw min. So that way we have 4 coordinates to define the window. Now, when we go to the viewports, now viewport is a rectangular part. Viewport is a rectangular part of the screen normally, where the drawing being displayed. Viewport is used to display the drawing. Normally, these viewports are defined in normalized device coordinates. These viewports are normally defined by using normalized device coordinates. The whole drawing area has corners 0, 0 and 1, 1. That way we can consider. Now, when we consider about these coordinates, we can set viewport x viewport min, x viewport max, x viewport, y viewport min and y viewport max. Same way we can have 4 coordinates for that. By using this one, we can get the dimensions of viewport and dimensions of window. Now let me start by clipping. So the clipping normally is the process of eliminating the things which are outside the window area. So once the window area is defined by using 4 corners, we can determine what are the things outside here. This is outside. This is outside. We can eliminate them. And we can take the clipping part. Now this clipping has to be done by some kind of a program or algorithm in the graphics. For that purpose, we have clipping algorithms. What are we doing by the clipping algorithm? Eliminate the outside area of the window inside the graphic. By considering the graphic, outside the window area will be clipped and removed. To clip and remove those pixels, we should know how to calculate and tell this is outside or inside. The first algorithm what we do is we are looking at point clipping. Eka point ekak, eka pixel ekak මේක ඇතුළේද එළියද කියලා තීරණය කරන්න කෙසේද? So how to determine whether that pixel is inside or outside of the window? That is very easy. How? If that x coordinate is in between x minimum and x maximum, x minimum is here, x maximum is here. If this is inside this one, and if this is inside this one, y minimum and y maximum, that is somewhere here. All the other things are outside. If x coordinate is in between x minimum and x maximum, and y coordinate is in between y minimum and y maximum, yw minimum and yw maximum, then what we do is we save that x1. We save that x comma y. Otherwise, what we do is, we remove that. We clip and remove. We clip and remove. Right? We remove that. So this is very simple algorithm, and both need to be satisfied. එකක් හරි fail වුණොත් මේකට වැඩි අඩු වෙලා හරි මේකට වැඩි වෙලා හරි නැත්නම් මේකට මේ අඩු වෙලා හරි මේකට අඩු වෙලා හරි මොකක් හරි එකක් වුණොත් මේක save කරන්නේ ඒක එළියේ. We clip it. And condition is there. So that is how we consider pixel by pixel, whether it is inside or outside. Is that clear and understood? Yes or no? Yes or no?
Yes.
Is that understood? It's very simple. Now, when you have a graphic, like line or some kind of a drawing, can we do it by pixel by pixel? Now, those pixels are on the memory, right? Memory, you have the values. Is it efficient? Whether we have to go through each and every line. Sometimes we drag and draw different things and we remove. Each and every time, if we have to go through each and every pixel to determine whether this pixel or this, for example, think about these lines. Set of lines are there. Can you see those lines? Yes or no? Hello? Can you see those lines? Hello? These lines?
Yes, sir.
Now, if we are going to consider these lines one by one, pixel by pixel, it is time consuming and lot of time to be wasted. Because pixel by then the algorithm is going to be highly inefficient if you are going to do it by point by point. Therefore, line clipping, there is a separate efficient algorithm is available. For the line clipping, there is a separate special algorithm, efficient algorithm. We call that one as Cohen-Sutherland line clipping algorithm. But it is Cohen-Sutherland line clipping algorithm. Now, these are the areas you have to remove. There's another name called for this particular algorithm, Cohen-Sutherland's outcode clipping algorithm. Outcode clipping algorithm. Because it uses a concept called outcode concept. It uses a concept called outcode concept, where the outcoding mechanism is used, very efficient mechanism, to determine whether line points are, line segments or line areas are outside or inside. That is a very efficient algorithm. So this is very efficient method for accepting or rejecting lines does not intersect with the window edges. Right, now what we are going to do is, we assign a binary 4-bit code to each vertex. We assign a binary 4-bit code to each vertex when we are working with this outcode clipping algorithm. First bit, we take 4 bits. Four bits, right? We mark it. Now this is the 4 corners, window area. These areas are marked 1, 0, 0. The first bit is 1. Now here these are the conditions. First bit is 1 above the top of the window. If any area is in this area or upper area here, anything upper than this particular line y max වලට වැඩිය විශාල ඕනම තැනක first bit is 1. Second bit is 1 when it is below this particular y min. Below y min anything, first bit is 1. Third bit is 1 to the right of the edge. Anything which are available in this area, third bit is 1. Fourth bit is 1, anything available in the left hand side somewhere. That's how you take the 4 bits code. Now let's see. This is the area. Above is 1. When you consider anything above this one. Below is 1, the second bit is 1. All the points. Anything right, 1 here. Anything left, 1 here. Others are zeros. Then here you can see the center, you have 0, 0, 0. Right? Now in the Cohen-Sutherland's algorithm, first what they do is anything less than x min, fourth bit is 1. Anything higher than x max, third bit is 1. Anything higher than y max, first bit is 1. Anything below than y min, second bit is 1. Like that you have 4 bits assigned here. Like that you have 4 bits assigned here. Now what we are going to do is, now we consider the 0, 0, 0 area. At the center area. That is the center area. We accept anything if the points are like this. Now our target is to clip the lines. Okay, let's consider this set of lines. We know that if there is a line, that line is defined by 2 endpoints. ඕනම රේඛාවක් අපි එක ඉගෙන ගත්ත line එකක් තියෙනවනම් line එකේ starting point එකයි end point එකයි තියෙනවා. Now what was the problem earlier for the point clipping? Each and every point we have to consider. Now we should be able to reduce that comparisons. Reduce the computation. We should be able to reduce the computation. That is the computational efficiency we are expecting. Now in this case, all the points having these endpoints. Now what we do is, for the endpoints of all the lines, we are putting the outcodes. The outcode for this one is 1, 0, 0. Here 1, 0, 1, 0. The first thing is we are marking the outcodes. Zero, 0, 1, 0. Here we take 0, 0, 0, 0. 0, 0, 0, 0. Here we take 0, 1, 0, 1. Here also we take 0, 0, 0, 0. Here 0, 0, 0, 1, 0, 0, 0, 1. Right? Now outcodes are done. Now what are we going to do? Now we know the outcodes of all the lines. Now how many points have we considered for the 8 or 5 lines? Only 10 points we have considered and put the outcodes. Now that is a simple one because within one line we don't know how many pixels are there. Maybe 1,000 pixels available within one line. 10,000 pixels available within one line. Who knows? How can we calculate that much of things? No, we are not going to calculate that. Only these endpoints are calculated. Now we are telling algorithm rule 1. Rule 1 of the algorithm is if both endpoints are within the 0, 0, 0, 0, we take that particular line as a line which is inside the window. That is this one. If both endpoint codes 0, 0, 0, 0, we take that consideration into trivial acceptance and that line will be accepted and taken in. Now, what are we going to do with the other lines then? Other lines do not have both 0, 0, 0. What we do is we do the logical AND of the outcode. What do you mean by logical AND? Logical AND means bitwise AND operation will be performed. Bitwise AND operation of the two endpoints. May endpoints dekhe thiyena outcodes wala bitwise AND operation. Let me tell you, I will draw it by using different color. I will mark it by using magenta or maybe yellow or no, green. I will mark it, okay, black. I'll mark it by using black. Bitwise AND means 0 into 0, 0. 0 into 0, 0. 0 into 0, 0. 1 into 1, 1. 0 into 0, 0. 1 into 0, 0. 0 into 0, 0. 1 into 0, 0. 0 into 0, 0. 1 into 0, 0. 0 into 1, 0. 0 into 0, 0. Here also 1 into 1, 1. 0 into 0, 0. 0 into 1, 0. 0 into 0, 0. This is the logical AND operation. Can you see my logical AND operation values available on the screen? Yes or no? Can you see it or not?
Yes, sir.
You can see, right? Now it says, now these are the positions you are having 0, 0, 0. This is 0, 0, 0, and this is 0, 0, 1, 1, 0, 0. These are the AND operations. Now it says, if one of the bit after logical AND operation, after performing the logical AND operation, this is already accepted now. After performing any logical AND operation, right? After performing logical AND operation, if one of the bit is 1, if the one of the bit is 1, that will be taken as trivial rejection. That whole line will be rejected. That whole line will be rejected. Now we don't know whether 1000 pixels or 5000 pixels or whatever the pixels, we are rejecting it. We are rejecting it. Okay? We are rejecting. That whole set of pixels, that line will be rejected. Whole line will be rejected in this case. Okay? And now what we are going to do is, we have two lines. For the rest of the lines, we are considering what are the intersections. What are the intersections? Right? What are the intersections? Like this one, we are checking the intersections. We are considering the intersections. So intersections will be taken. So those intersections and we mark it. Right? We mark it. Right? And then for these intersections, we mark the outcodes again. We mark the outcodes again. Right? We mark the outcodes again. And again for those outcodes, we are doing the logical and we eliminate this part and this part. And also this part and this part, because outcodes are going to be, again, you are marking for these segments. We are taking the intersection by using ymin, xmin, ymax, xmax. Ymin, xmin, ymax, xmax. We are marking the boundaries and then put the outcodes. Right? Then what you can say is that these outcodes can be multiplied with 1 by 1, and here it will become 0, 0, 0, and trivial acceptance can be there. This is logically, and after putting the logical and this particular point will become 1. Here when you put the logical and this point will become 1. This one, and here this one will become 1 when you put the logical line. And these things will be eliminated. This part and this part will be inside the window. That is how the consider the intersection line segments with edges of the clipped rectangle and select any clipped edges, trivial line splitting, feed 2 line outcodes back into the algorithm and see whether it is working. Now, by considering this one, this is the way we can see the algorithm. Input 2 line endpoints. Right? First, what we do is we feed 2 line endpoints. Obtain the regional codes of the line endpoints. If both endpoints are in the 0, 0, 0, that is the first thing we consider. Then line is completely inside the window. Save it. If both endpoint regions codes have outcodes multiplication gives 1 at the same bit position, then clip the line completely outside the window. If 3 and 4 are not satisfied, obtain the intersection points from the x equal xmin, x equal xmax, y equal ymin, y equal ymax, and cut them and you get the intersection points of those lines. And for the respective line segments, put the new encodes and check it against 3 and 4. 3 and 4. This one and this one. Again, we are repeating this. And then what you do is you can get the part which is acceptable, other part which is rejected. That's how it works. And this is what we call as Cohen-Sutherland outcode clipping algorithm or Cohen-Sutherland's algorithm. Any questions about Cohen-Sutherland's algorithm? Any question? Any question? Hello? Any question? Okay. Right, let's move to the next one. Now at the beginning I told you, now in the Windows, the viewing pipeline, two-dimensional viewing pipeline, starting from the memory, we are clipping it. After clipping, that will be available in the window. Now we have clipped and taken that sum of the graphics into the window. Now this window is shown on the screen as a small viewport like this. Now how are we going to map these pixels into these pixels? This viewport is the thing we can see in the normal device coordinate system. Normal device coordinates means the device that display, screen, LED, LCD, whatever the cathode ray tube, whatever the display device. How are we going to transform it? That is what we are going to consider. Now in the window, each and every object here, if you take any pixel here, that pixel got a coordinate with respect to this window. Now what is the coordinate in this viewport? We have to calculate. Where are we going to put this pixel? Here. Somewhere here it may be there. So consider one pixel here. Where should we put that pixel in the viewport? We have to decide based on the dimensions of that window and the viewport. In that respective manner, this is Windows coordinate, the Windows world coordinate system. This is normalized device coordinate system. Normalized device coordinate system means screen. Here we are working with world coordinate system. In the world, this XW, YW is available with respective to the XW main, YW main, XW max, YW max. Right? Here the XW max, YW max, XW main, YW main. What is the coordinate here? XW main, YW max. What is the coordinate here? XW max, YW main. Now these coordinates are with respective to world coordinate system. Now what is the coordinate of this point with respect to the window, this distance? What is the coordinate of this point, y coordinates of this point with respect to the window, this part? And here also we have yx viewport xv max, yv max. xv mean here and yv mean also here. Same way you can have coordinates here. Now the same xw, yw is available here now. Same pixel, that is our assumption. Now what is the coordinate of this point with respect to the viewport? These distances. xv minus xv mean yv minus yv mean. xv minus xv mean yv minus yv mean. That's how it is available. xv minus xv mean and yv minus yv mean. That is how these coordinates are available. Right? Now, if the same point is available here, the viewport window, the full window to be transformed to here, we are considering that this particular length to this particular length ratio should be equal to this particular length to this particular length ratio. Similarly, if you have the ratio in between this particular length and the window's length, this particular height to the window's height, these two ratios should be equal to this particular height to this particular height ratio should be equal to this particular width to this particular width ratio. Okay, let me take the x1. This length to this length ratio should be equal to this length to this length ratio. This height to this height ratio should be equal to this height to this height ratio. That is the norm we are taking. Therefore, we can write xw minus xw mean, this distance. Xw max to xw mean, that is this distance, this ratio, should be equal to xv minus this one, xv minus xv mean, divided by xv max minus xv mean. This ratio to this ratio, these two equal. Then if you know what is the point on the window's coordinates, if you know the length of and width of the window's coordinates, that window, width of the window, if you know the width of the viewport, you can calculate where is the point you have to place in the viewport. Same way, yw minus yw mean this height. Yw max to yw mean this height. Yw minus yw mean this height. Yw max minus yw mean this height. This ratio should be equal to yv minus yv mean, yv minus yv mean, divided by yv max minus yv mean, yv max minus yv mean. This ratio to this height ratio, these two should be equal. If we know the yw, we can calculate, because we should know what is the height of the viewport, height of the window, and the location of the window point. Then we can calculate the corresponding point on the viewport. Therefore, very easily, by using this type of equation, we are able to transform the window's coordinates to viewport coordinate. So window's coordinate, we can capitalize the window's coordinate and the viewport coordinates. And in terms of window's dimensions and viewport dimensions, and the window's point can be calculated where they're placed in the viewport. This is the equation for doing that. If you were given that such situation, you should be able to calculate by using these two equations. Right, so same thing is available here. So the final thing what I want to say as a summary is, the world coordinate system, we are creating very big graphic that is coming in the world coordinate system here. Window is coming in the world coordinate system. And that world coordinate system map the window, and we clip the graphic, and we identify the window within the world coordinate system. The points which are on the world coordinate system in the memory, and that map to the viewport by using these equations. Those points which are inside the viewport window, and then we place them into the screen pixels, and we can eliminate with that particular color. That is what we called as 2D viewing pipeline, which are available on the memory. From memory, we clip it. After clipping, we take and map them to the viewport, and viewport will be placed on the screen, and we calculate where the pixel to be illuminated and what is the color of that pixel. As a whole, we do that. That is what we called as two-dimensional weaving pipeline of the computer graphics. Okay, if you have any questions, you can ask now. Otherwise, we can wind up today's session. And next day, I am directly starting with CorelDRAW, rest of the things, and then I will jump into the Photoshop and the two-dimensional graphics to be completed. Now I have completed all the things which I need to cover within the two-dimensional graphics. And next day, we are going to do the two-dimensional graphical applications. And after that, I will start the three-dimensional graphics.